very much in the vein of a discussion because it's actually ongoing work, work which has been precipitated partly by a lot of controversy on this subject of disk clearing in the last year as a result of results of ongoing Spitzer surveys. And as you may know, James Owen and Barbara Colano and I have been doing a lot of work on photoevaporation recently. And one of the observational goalposts for those kind of models is a belief that disks clear quickly at the end of their primordial phase. And I'll explain why we believe that, mostly going back to observations made in the late 80s, early 90s. And there have been completely different claims being made by a number of groups over the last year or so from the much larger Spitzer surveys. And so we're pretty interested to know whether we're actually aiming at the wrong thing observationally and trying to understand the whole context in which we're working. Exactly. So that's the motivation behind it, and we've been helped by on this project by Alex Hall, who's a fourth year undergraduate who's been working with us over the summer. But as I say, it is an ongoing project, so we won't necessarily have all the numbers and the models at our fingertips at the present time. So the conventional view of disk clearing, I don't know how familiar everybody here is with the whole sort of taxonomy of spectral energy distributions in T-Tauri stars, but the conventional view is that disks either possess active optically thick disks in the primordial phase, or they very rapidly then evolve to a state where they can only be detected as stellar photospheres in most cases. And you don't see many objects that are in an intermediate state between optically thick disks in the infrared and pure photospheric. And this is the argument basically for saying that you need some rapid event to clear disks at the end of their primordial protoplanetary lifetime. Just because we'll be showing quite a few SEDs, just to run through what you learn from SEDs, this of course is the stellar black body here. You've got excess emission in an object like this one, BP tau, from a number of sources. This UV excess is interpreted as excess emission associated with accretion onto the star. Over in the submillimeter here, the disks are usually somewhat optically thin, and so we can use that to measure the amount of mass in dust grains, of course, in the disk. Millimeter-sized dust is what you're directly probing there. And then at intermediate radii, in disks like this, intermediate wavelengths rather, in disks like this, the emission is very optically thick, so of course you're not learning about the mass per se, you're learning about the temperature distribution in the disk. And this will be set, if the disk is an active accretion disk, of course by the accretion rate, but in many cases we're looking at disks which are passively reprocessing the light from the central star. So in this case the temperature distribution, and hence the form of the spectrum here, is basically set by the geometry of the disk and the solid angle it subtends at various radii. So as I say, the old picture was that to first order, T-Tauri stars come in two flavours, things that look like this and things that look like stellar photospheres. There are exceptions. They number about 10% of the disk-bearing population. These are the transition objects, and this tells you that the transition timescale must be a short one, maybe about 10% of the lifetime that the disk has lived already. Let's just think a little bit about why disks should evolve anyway. Okay. There are a number of reasons why the SEDs of disks should evolve, such as being associated with grain growth, which affects the spectrum, the optically thin regime, or dust settling, which affects the disk geometry. But the zeroth order, in the more actively accreting disks, then the evolution has probably got something to do with accretion, and you just roughly take the accretion rates that you infer from the UV excess, multiply it by your estimates of the object ages, 1 million years or so, and you get something of the same order as your estimated disk mass. So accretion should be a major player in driving disk evolution. Now, I hesitate to start using the word viscosity in relation to angular momentum transport in disks because, of course, I'm aware that it's a much more complicated business than maybe a sort of alpha-style viscosity. But just as a sort of phenomenological level, we have accretion, we have angular momentum redistribution in these disks. And if we just take note of the fact that the surface density in these disks is observed to be roughly power law, say with some index A, then in an accretion disk scenario, you would then infer that your phenomenological viscosity, kinematic viscosity, scaled as the opposite power of with radius. And for those simple power law viscosity prescriptions, you can go back to the famous Lyndon, Bell and Pringle similarity solutions, and if you take a sigma going as r to the -1, which is roughly appropriate to most pre-main sequence disks, then you get a power law similarity solution decline of the accretion rate with time. And Lee Hartman did a lot of work in 1998 applying that to observations of disks as they were at that stage. And he argued it wasn't necessarily such a bad description, although clearly you've got far more than just all disks evolving along a single track. As Phil Armitage and I explored a few years ago, you've also got a lot of intrinsic scatter in the systems in terms of disk masses and disk viscous timescales. But it's not out of the question to say that when you look at a distribution like that, the overall timescale on which your accretion rate is evolving is roughly the age of the system, in other words, of order 1 million years. So it's sort of consistent with a power law type decline. And so then we want to know whether we can just let viscosity to carry on doing this way down past the observational limits at which you can measure accretion around young stars, and whether then that will explain the distribution of infrared colours you get around young stars as they get progressively optically thinner and thinner as they drain by viscosity. So can you just take this model and crank it forward in time? And the argument that you can't, I think this doesn't show up well at all. This is a two-color diagram which was first compiled by Kinnian and Hartman in 1995. It was then done in terms of K minus N and K minus L. We plotted them to the IRAC colours, but basically, if you could detect the green down here, these are the colours of stellar photospheres, late-type stellar photospheres, so they're relatively blue. All these objects up here are disk systems, and what you would see, if you could see, there's a gap in this region here. And it's an interesting place to have a gap because round about here are the colours that you would expect a disk, if it was completely optically thick and flat, those are the colours that a reprocessing disk with no accretion going on would have. So apparently we can understand this evolution that these redder disk systems up here are probably more flared, so they've got more emission at a long wavelength. They could have extra spectral components due to intrinsic accretion luminosity in the disk. But as a function of time, you might expect that both those two factors would go away, and so you'd move to blue and bluer disk colours. But once you arrive at being a flat, optically thick dinner plate, then there you will stay until finally you've drained down to such a low column density that you're becoming optically thin. But there you stay for a long time because you have to get down to a very low column density. And Alex Hall, when running these models of how power law self-similar disks would evolve in this diagram, he was basically taking power law disks, each colour mapping a set of models which had an order of magnitude lower in column density. And what you see that, of course, your models, as I say, sit for a long time with the colours of the optically thin, flat dinner plate, and it's only when they get down to column densities of about 10 to the minus 4 grams per centimetre squared at about an AU that they start to go across this forbidden region, if you like, this optically thin region here. And don't forget that if you have a power law decline, it takes longer for each successive drop in by a decade in surface density, and therefore in terms of the time spent in this diagram, you would spend a long time here and you would spend even longer crossing this forbidden zone. So that's why it's incompatible with just a simple power law decline with time, because you'd find most of your objects should end up down the bottom right of that bottom left of that diagram. And if you want to be quantitative, if you match these kind of curves which are producing you the reduction in accretion rate on about 1 million years time scales, and then say, well, how long would I have to wait if I didn't put anything else into there until your disk started getting optically thin? Well, that would be many hundreds of millions of years. So you should have optically thick disks sitting around main sequence stars, and then about a further 500 million years spent in slowly crossing that optically thin regime. So clearly that doesn't happen. So we can rule out just the viscous similarity solution being the main thing that chases away the end of the disk. You've got to have something else intervening en route. And of course there are lots of possibilities. We've been working on photoevaporation, but planets, of course, all you have to do is to remove the opacity in the relevant wavelength band. You don't necessarily have to dispense with the disk gas at the same time. Yeah.
So when you talk about similarity solutions, there's the similarity solutions where the viscosity is a function of radius.
Yeah, that's right. Yeah.
And it also depended on density.
Could depend on anything. Yeah.
You get a different kind of similarity solution,
Sure.
which I guess
It could, but I think I was only making that point that whatever phenomenological rule you make up, it mustn't end up with a power law as a function of time. So you've got to have something built into the physics that gives you a second, much shorter time scale. So that was really more illustrative of the effects of a power law, actually, than, of course, that's completely artificial. Okay, so that was what was driving us in trying to get rid of disks quickly at the end. And now this appears to have been muddied by recent Spitzer observations and stated perhaps most provocatively in this paper by Curry and collaborators that came out earlier this year. The subsequent papers by him that have stated it in a more understated way. But basically what he was saying is in the cluster that he was looking at, he had lots of objects that were in this intermediate state, and so he was arguing against the classical standard argument from Torres Origa that you go from one state to the other on a short, sort of 10 to the 5 year time scale. And so if this now turns out to be true, then maybe we don't need a rapid clearing mechanism. And there are a couple of reasons why the Spitzer observations might have led you to a different answer. Partly it's just sheer numbers of objects. The samples are much bigger than people were dealing with in the 1990s. And secondly, there's a rather different distribution of stellar temperatures, spectral types, in most of the clusters that have been looked at by Spitzer. There are many more cool stars, M stars, than you find in Taurus. So again, it could potentially be telling you something interesting about a spectral type dependence. And also, of course, it would indeed be very useful if there's a large population of these intermediate disks, because you actually learn much more about the disk when it's partially cleared. An optically thick disk is very uninformative, and a pure stellar photosphere is very uninformative. So actually each transition object is gold dust. So in some sense it's good news that there are apparently many more of them. But we nevertheless thought we wanted to take another look at the data and actually just understand why is the paradigm, apparently 6 months ago the paradigm was in the process of flipping. I'll show you why it's probably sort of flipping back again. So another diagram which became rather hard to read. This is what puzzled us in our initial look at this, is that we thought if these other clusters are behaving completely different from the old Taurus data, they should look really pretty different in this two-color diagram. So that's what I showed you before, K minus 8 and K minus 3.6. This is the Taurus data, and although we cleaned this object so as to remove the odd binary that sat in there, if you take the statistics that were available prior to the Spitzer surveys, you would have put a few transition objects in this gap and come up with the conclusion, as I said before, that maybe 10% of these guys actually resided in that region. But here's the data put together, all the different Spitzer clusters. This is one of the things that Alex is doing over the summer. Here again is the location of an optically thick dinner plate in that diagram. And again, you've got about 10% of this total are sitting in this region. So we're not obviously just looking at this particular diagnostic, seeing anything that's glaringly very different about these stars in the two-color plane. What we expected was to see a huge population in here. They're not there, and in fact many of the objects which have been claimed to be so-called anemic disks or homologously depleted disks, various terms that have been used to describe this new large population of intermediate type disks in these Spitzer surveys. Many of them, when plotted up in this diagram, were up here with the colours of optically thick disks. So this seemed a bit puzzling to us. And there are a number of elements. We haven't completely got to the bottom of this, but let me just tell you some of the things that we've discovered. So one is that there's a systematic effect on the contrast between the disk and the star. If you take a pure reprocessing disk and you go to cooler stars. So obviously if you go to a cooler star, your star's going to be fainter at a particular wavelength, but the region in the disk producing that particular wavelength will be smaller, and therefore there'll be less disk emission. And if you're all armed with clickers, I could ask you which you think would go down more as you reduce the temperature of the star. You can actually sort of derive it in about 2 lines, and of course it depends on what the radial profile, the temperature in the disk actually is. But because the radial profile is relatively flat in these reprocessing disks, it actually turns out that if you reduce the temperature of the star, you reduce the region of the disk from which this particular wavelength of emission is coming a lot, and therefore the ratio of the disk out of a given wavelength in a reprocessing disk to the star at that wavelength actually goes down as you go to a cooler photosphere. So the issue with that is, so here again some spectral energy distributions. These are taken from a paper by Cecilia Aguilar et al. 2008 in the Coronet. This is Thomas Henning's group. A claim for a very large fraction of disks apparently with inner holes inside them. The claim from that paper was that I think it was 50% of disks in the coronet have inner holes, by which they meant no excess emission from the disk at these wavelengths and yet plenty of emission out there. But in fact, this turned out almost certainly to be an artifact of the fact that you just don't have the sensitivity to detect a reprocessing disk about an M star above the photosphere if you go to too short wavelengths. And our fits to the SEDs of these objects are perfectly fit by reprocessing disks which don't have a truncation other than the obvious truncation that you truncate the dust at the dust sublimation radius. And so the reason it looks like an inner hole system is because you're not seeing the disk above the photosphere below about 6 microns is what it turns out to be for stars of this temperature. But that's not really evidence that there isn't disk there, it's just well, you wouldn't see it anyhow. So we were able to, by running models from Tom Robitaille's library of SED models, we were able to show that many of the claimed transition objects in the coronet actually were nothing more interesting than dull, rather flat, optically thick disks, but some of them were bona fide inner holes. But as I say, I think there's a systematic here because the Spitzer surveys have got more cooler stars in than the original Taurus survey, and therefore more objects looking like this in things that aren't inner holes masquerading as inner holes were turned up in these later surveys. So that's one part of the argument. The other one is that sometimes when people say, well, we've got a very high fraction of partially cleared or anemic disks, it's just a kind of empirical statement that they've got much less infrared emission than the median value in Taurus. So here's all the SEDs of the Taurus sample. Here's the median plotted here. And this is what you'd get from your flat optically thick disk. So you can have plenty of optically thick disks around stars which are still significantly less luminous at these wavelengths than the Taurus median, but that doesn't actually mean to say that you've identified disks which are giving you evidence of being in a sort of partially cleared state, if you like. What it almost certainly does mean, of course, though, that if these clusters are looking very different from Taurus and they're actually much weaker in the infrared, it's probably a sign the disk geometry is different. But we're not the first people to be saying this. There's been a number of studies that in recent years looking at later type stars like Daniel Appé and collaborators and Ilaria Pascucci as well, making the argument that the later type stars, the dust is more settled and therefore you would get a steeper spectral energy distribution in the infrared. And one of the other things is that people are claiming that they've detected some very low disk masses through these Spitzer samples. They fitted their SEDs and are coming up with very low masses, impossibly low for there to be any further ongoing planet formation. But I think one has to take these claims with a certain amount of caution, because in most cases they don't have data longward of 24 microns. And it's very difficult to unambiguously get a disk mass from a 24 micron point, even when combined with the rest of the SED. And part of the reason, of course, you've got a degeneracy between disk mass and the temperature profile. You may, for example, the slope of this, by the way, is pretty close to the lambda f lambda goes as lambda to the minus 4/3 that you get for a flat reprocessing disk. So that may turn out to be a potential explanation of the SED of this object. This is one of Thane Curry's objects where he's saying that he's got evidence for partial clearing. So as I say, it may just be another one of these boring dinner plates where you can't tell anything about the mass inside. On the other hand, it could also be, what he's managed to fit successfully is a flared disk model which is somewhat optically thin. Even if you think you know the geometry for some reason and then try and see how the predictions at 24 microns scale with the mass, it's a very, very blunt tool for measuring disk mass. And here's some models that Barbara's just run, 4 orders of magnitude in disk mass. Here's a 3 sigma error bar on the 24 micron flux. So really, it's unfortunate, of course you need data points out here to get the mass, but I think it's a bit of a lost cause probably to derive sort of anything unambiguous from a spectrum that only goes as far as there. And a further real sort of beware that we've learnt over the last few months working with Tom Robitaille's SED model libraries. And actually at Jim's conference in September, he was very clear, I think, about the ways that his models can be used and abused. And this is the thing that he warned us about, that of course he can't sample the whole of parameter space, right? So he has some theoretical prejudice in the combinations of parameters that he puts into his library. And so sometimes the thing that you think you're measuring, you're actually only measuring it because it's associated with certain other parameters that are really determining some important feature of your spectrum. And in particular, if you see a disk like this, which is claimed to be partially cleared, to have got rid of most of its mass, it doesn't have much accretion luminosity in the spectrum. So you're looking for models which have very low accretion rates, but in the model library, they're also correlated with models which have very low masses. And so you might get very low mass model fits coming back. So, I think they're an excellent tool, but they have to be run with extreme caution. And I think just reading the papers on the subject over the course of the year, I think people are learning this quite fast. But there's an excellent paper that came out last week by James Muzzerall and collaborators, which I think will do a lot to sort of clean up the field, because what we really want is some kind of simple empirical classification of disks in different states. And he proposed just that the classical transition objects, the objects where you've cleared at small radii, and this basically means at about the AU scale, so it's obviously very interesting for planet formation, these should show up in the spectrum as a rising flux between 8 and 24 microns. And certainly all the model runs we've done, the objects we've looked at, that turns out to be unambiguously the case, that if you see a spectrum that does this, that is indeed an inner hole. And then there's a large population of other objects, which in a few clusters have been claimed to be up at the almost 30–40% level. They're a more mixed bag. He calls them weak excess, and that means you can't see any emission above the photosphere in the near infrared, but they have some emission at larger radii. And like this one, so again, this one seems to have the spectral slope of a flat reprocessing dinner plate, but they're a rather mixed bag of objects. So the sort of provisional picture that I would be evolving towards is that actually these are objects which are just settled. They're late in life, their accretion rate's gone down, and they're spatially settled and thin. You can't learn very much about what's going on inside them. And then at some point, something, photoevaporation, planet formation, whatever, grain growth, leads you to this object. And the superficial problem with that scenario is that very few of these are accreting, and about half of these are accreting. So how can you have an evolutionary scenario where one of these turns into here? You don't actually expect accretion to be turning on when you create an inner hole. I think that's probably an apparent paradox, just because of the different spectral types of the stars of which these two types of transition objects predominant. So again, this is from James Muzzerall's excellent recent paper. This is the incident, forget about the black and the white, this is sort of slightly age differences between clusters, but just look at the overall histograms. This is the incidence of the classical TOs, they're the things with the holes in the middle, as a function of spectral type, and this is what you think the IMF's doing. So in sort of fractional terms, these objects with well-defined holes in them are commoner in the earlier spectral types than the M stars. But if you then add in all these weak excess objects, which I'm arguing are the sort of late quiescent, optically thick, flat guys, then they really dominate by a large factor when you get to late spectral types. So broadly speaking, At late spectral types, your average object, which isn't a booming, strong classical T-Tauri star, is much more likely to be one of these weak excesses than a classical disk with a hole in it, whereas for more massive stars, the more usual route is to create a well-defined inner hole. So this is my last slide on this, is that where we're going to now is, here's a working hypothesis. Or something I should have just shown you from James Mazerol's analysis in that last week's paper. The one before. Oh yes, important piece of information here, that when you've classified them like this and just taken out the ones that really are holes, their incidence is 10%. So you get back to the same argument that you want, if you create an inner hole, you want a short lifetime for that, a quick dispersal mechanism. So that's what the statistics are saying. So the working hypothesis is that we can go back to saying we need a short transition time, we need to open up a gap and propagate it out and clear your circumstellar material on a short time scale, about 10 to the 5 years. But we have got this phenomenon that hadn't been noticed before in Taurus, because there aren't many M stars, that when you go to later type stars, you find a lot of flat, quiescent, optically thick disks, low accretion rate. And so our idea here is that what this is showing you is actually the transition, the final inner hole or whatever, and growth cuts in later for M-type stars, and therefore they've already spent longer in this sort of intermediate state at the moment. So that's all I prepared on this. The idea, I thought, was we can discuss this if you like, and then because James and Barbara and I have been doing quite a lot of work on X-ray photoevaporation since I gave a talk at the kickoff meeting, they could just show a few slides just showing you some latest results on that. But this is more a general thing, because it's not really tied specifically to photoevaporation, but our conclusion is anyway that we still ought to be sort of aiming at the same kind of observational goalposts, because after all the data is saying that you only have these inner holes in about 10% of young stars. So does anybody have any comments or questions or arguments about that? Yeah. Jane?
This could be related to planet formation, because there's a lot of theories that planet formation would be difficult around very low mass stars that start with quite low mass disks. I wondered if you might have found a transition between the planet forming stars and the non-planet forming stars in some sense.
It could be. I mean, the disk still has to go away at some point, because you don't want optically thick disks around M stars at
right,
50 million years.
Build some boring big rocks so the signal fades, but you don't get anything planet size. It actually mops everything up and makes a hole.
Yeah, you certainly don't have anything happening as quickly, would be my... There is a slight possible observational slant on this, though. Sorry, I'll just pull that up again. Just in terms of detection. I said you don't tend to see the sort of classical inner holes so much among the M stars, but that could just be because they've already faded away down to there by the time the hole opens. So you could get a planet forming, say, I don't know, 10 million years or whatever in here, but it wouldn't give as much as a well-defined signal in a star that was already very weak out 24 microns anyway, as one where it cut in at an early time when the disk was, accreting and flared and all the rest of it. But yeah.
Probably the Herschel data is what will help out there.
Absolutely.
Start getting data at 70 microns.
Yep, that's right, yeah. And people are going after these things with sub-millimeter, but you're not getting down much below a Jupiter mass in the sub-millimeter. Can you? Well, the proposals I've seen are not, but you have a clever way. Yeah. Barbara, do you want to?
I can start setting up because it's going to take me out.
Sorry?
I can definitely stop.
Yeah, well, yeah. I mean, get going because yeah, I think the next thing I'll do that. You want to get? You do that. No, we're done.
Can I?
Yeah. Yes, absolutely. Yeah, I'm sure.
Last chance for questions.
What are the size of the holes compared with co-rotation?
Outside. Yeah. considerably. I mean, you wouldn't detect a co-rotation-sized hole.
Yeah, it's too small.
Yeah. Actually, interestingly enough, that's one of our early models, Phil Armitage and I, on trying to explain inner holes through getting the magnetosphere just winding the disk out once it goes outside co-rotation. But we couldn't get it to move quickly because you're still limited in that process by the viscous timescale upstream of where your magnetosphere is.
Help.
Cathie, can I
Yes.
just ask a question? So what are the
Oh,
prospects?
sorry.
I need some more.
She needs some technical help and then I'll answer your question.
Technical help.
Can you please come through? Yeah. Okay. Yeah.
What are the prospects in the next few years for having good data on dispersal times as a function of spectral types? And you seem to be indicating that there may be some trend to go to lower mass stars. It's taking longer for disks to disperse, even though you can't actually see it that easily.
Yeah.
But are there good prospects for being able to nail that down and to show a correlation between dispersal time and stellar type?
Yeah, I think just as you go to longer wavelengths, as you get Herschel data and ALMA data, you'll obviously be able to characterize these disks at the end of their lives and make much less crude assessments of what is cleared and break the model degeneracy. So I think that's going to be the main thing. In terms of the general question of lifetime as a function of spectral type, I mean, already that's known in a sort of broad brush way that as you go to early type stars, the lifetime goes down.
Indeed.
Yeah. But not so much maybe about relative timescales, just in terms of kind of...
What about the comparison between, say, G-type stars and M-type stars? Is there clear data on that for the timescales for clearing?
Yes, the M stars do tend to last longer. Yeah, so there are certainly clusters at sort of 6-7 million years where most of the early type stars are now weak-line T-Tauri stars, but the M stars have still got some of these dull flat disks on them.
Are we talking a factor of 2 in timescale or an order of magnitude?
I think more like a factor 2, and so one's scepticism about knowing ages then starts to creep in, except in a way, even if you don't know the ages, if you see that one object has gone and the other object's still there, that tells you that it lives longer, so that's okay.
Question.
So when James says that there's no accretion, no evidence of accretion in the M star,
Well, 3 out of 20.
or very little, is that relative to the expectation of accretion would scale with the mass, or relative to the observed sort of median accretion? Because this is sort of
My
M
guess.
squared or
Yeah,
steeper,
yes.
so you could easily imagine in an M star that you don't need to drop very much. And
My guess is that it's purely that, but all they've just haven't measured accretion rates as such. They're just using some criterion on strong ball H alpha that's been detected. That could just be what you'd expect for a sample of M stars. Period. I don't think he's actually done a comparison between them and the M stars which have got healthier disks. Which is what we've done.
Okay, so I'm going to take the stage. Basically, I'm going to start with the conviction that everything that Cathie said is right, and therefore we do need the 2 timescale scenario for this dispersal. So we're going after a process that leaves the disk being for a few million years doing absolutely nothing and just looking optically thick, and then just disappearing. And so one of those, of course, is the old photo operation, which in its previous incarnation has had a lot of, let's say, things that couldn't explain some low photo operation rates. And we have re-explored everything with X-ray radiation. And so what I'm going to show today is stuff that Cathie had already showed at the beginning at the kickoff conference for the Newton Institute meeting, but some of you weren't there. So I'm just going to show a couple of slides on that, and then I'll show you what we've done since then. And so we've been running radiation hydrodynamics models of basically T-Tauri's disks irradiated by X-rays from the central stars, where the X-rays from YSOs, of course, have just come in from chromospheric emission. And what I'm showing you here, I'm not giving you any detail at all of that calculation, and I'm just showing you the results. This is just the density structure of one of such disks, where you see the disk and its wind, and the solid lines just show the streamlines. So what we found was that the mass loss rates that we calculated, this is work that has been mainly done by James Owen, so he should actually have been presenting this. I don't know, we have kind of mixed up all the work here. But we found photo-operation rates of the order of 10 to the minus 8 solar masses per year. And that was very encouraging because it's very similar, of course, to the accretion rates for many of the classical Titori stars. And so this pointed to the fact that X-ray photooperation should really not be discounted as being too weak in any case, and in fact is probably a very significant dispersal mechanisms for disks. So encouraged by these results, we went on and coupled our photooperation rates with just a simple viscous evolution code. And what we have is this very simple high-tech video of how a Titori disk actually evolves. And I'm going to stop here for a second just to show you what's happening here. What I'm plotting here is just the surface density of the disk as a function of its radius. So here is the inner disk, and here is the outer disk. And I'm going to let it evolve as a function of time. And so what you have up here is actually time as a function of as a fraction of the disk lifetime. Because of course, absolute time scales are just decided by the parameters that you use for viscosity, et cetera, et cetera. So we have an alpha disk here. So what you will see is that we do see this 2 time scale behavior. The disk starts evolving, and for a large fraction of its lifetime, it's just being optically thick, doing nothing. All you're seeing here is just viscous evolution. And the reason for that is that when the disk is young, it's accreting at a rate that is much higher than the photooperation rate. So the disk is photooperating, so there is a flow, but it doesn't actually know that it's photooperating because it's accreting at a much faster rate. And that's what you see for most of the disk lifetime. So that allows you to go out and see disks being optically thick for a few million years. And it's really not until you get roundabout here, this is now like 60–70% of disk lifetime, I'm going to stop it for a second, that you start seeing a flattening of the surface density. So this is when the accretion rates are comparable to the photooperation rates. As the accretion rates actually draw even lower, at about 1/10 of the photooperation rates, then you see that actually photooperation can draw the classical gap into the disk. And what you're left with at this point is the inner disk and an outer disk. Now, this is the point at which you would already detect a gap in the dust distribution. But at this point, I should stress out that you will still see gas in the inner disk, and you will still see the disk as accreting. And so for a significant fraction of the transition disk lifetime, you actually see gas in the inner hull that is draining on the viscous timescales, and you will see some accretion rate. And I'm stressing this because in previous papers, but also at various conferences, there is the usual observations of a transition disk with gas in the inner hull and says, okay, this is a planet because we can't explain this for photooperation. That's not necessarily true. It may, of course, be true that some of those transition disks are made by planets, but seeing gas and an accretion rate in a transition disk is not necessarily a showstopper for photooperation. And so this is just my very quick summary of James's first year PhD work. And I've just mentioned that, of course, we're not claiming that all transition disks are made by photooperation, and that some of them will actually be disk gaps that are made by planets. But that's probably not really the issue now. The issue is not really trying to understand this particular transition disk or that particular transition disk. The issue is actually trying to understand what is the dominant dispersal mechanism. Because once we understand that, of course, we can make prediction of how this would occur in different environments. And so we can actually make prediction that give us input parameters for planet formation models. And so one way to discriminate between clearing mechanisms, so this dispersal mechanism, would in fact to try and actually predict how they would behave in different environments. And one obvious different behavior between planet formation and photooperation would be to look at it in places of different metallicities. So this is what we've done in this paper that's recently been accepted. And what we found exactly what we expected, that the mass loss rate in a disk with a lower metallicity would be much, much higher, which of course translates in a much shorter dispersal timescale. So that's intuitively true that, of course, you have a lower metallicity, you have a higher gas temperature, so the stuff goes out quicker. But it's actually this particular behavior with a significant slope, it's quite a shallow slope, but it's still quite a significant slope, is actually due to the fact that it is gas that is being heated by X-rays. And I'll explain why. So this is the temperature structure in our disks, 1 AU. And this is plotted as gas temperature against the column density. So here now you have the disk surface, and here you have the disk midplane. So when you look at the temperatures, which correspond to disks of different metallicities, you see that for the lowest metallicity, which is this one, you can carry the X-ray heating quite a way into the disk. Whereas if you increase the metallicity, then you're just limited to the surface of the disk. And this is just coming out from the fact that by lowering the metallicity, you are significantly lowering the opacity for the X-rays, because X-rays are predominantly absorbed by the K-shells of heavy elements. So I stress that this would not be happening if you had EUV photooperation, or if you had an EUV photon that hits the disk of lower metallicity. All it cares is the hydrogen. So if you don't change the hydrogen, and of course it cares about the dust, but it's a smaller effect. So because you have X-ray heating, you actually have this very large behavior here. And so what would planet formation instead do? Well, we used a very, very rough analytical approach, just using the either Lin scenario, and just basically said, okay, when you form a gas giant by co-accretion, this is when the disk goes. And because we're not actually interested in absolute timescale, we're just interested in seeing how this would vary with metallicity. And so by making all this approximation and thinking of planet formation in different regimes, we can still express this as a power law of metallicity. And this time the slope is actually negative, so it's the opposite of what photooperation gives you. And it's actually quite a steep slope. I mean, of course, these are very, very ridiculous slopes. But even when we compare this with actual hydrodynamical models, we see clear indication that there should be a negative slope. And we can just guess that there should be a negative slope, because if you have a slower metallicity, you have obviously less dust, you don't have anything to make planets with. So that's basically all that we're saying here. And so the suggestion in the first version of this paper, which luckily we didn't submit in time, was that, oh, this is really interesting, but it's probably irrelevant because nobody can go and look at disk fraction in the LMC and SMC because it's just too far. But then we wasted some time, so we didn't submit when we wanted to. And observational, well, let's say pioneering observational evidence did come through in the form of these Japanese authors, Yasui et al., which looked at disk fractions in clusters in the extreme outer galaxy. So these are clusters with about 0.1 or 0.2 of the solar metallicity. And to my great amazement and almost disbelief, they did find something quite similar to what we predicted. So I actually don't believe in any, I'm not trying to claim at all that this is, oh yes, we got it right and we got the slope right as well. But at least it seems that we got the sign of the slope right, which is really what that matters here. Because if the dominant dispersal mechanism in these clusters had been planet formation, then you wouldn't see this positive slope here at all. You would see quite a significant negative slope. So we were quite intrigued by this. And as I say, I don't think it's the end of the story. We hope that this work will now encourage other people, observers, to try and bring these observations forward, since this could be a really nice way to discriminate between these two models. And I'm actually not going to say anything else here because I want to leave some time for James, who will actually talk about some more convincing evidence for photooperation in the form of a smoking gun of a photooperating wind in line profiles. So I will stop here and take questions if you have any.
So given that the X-rays may also be penetrating the disk and ionizing it, they could therefore affect alpha value in the disk. And I think I'm right in saying that they would penetrate more deeply in a lower metallicity disk, and therefore you might expect faster viscous evolution as well. So that would go in the same direction, I think, as what you're suggesting, which is you get faster photoevaporation as well as faster viscous evolution. So just wondering whether it's possible to differentiate between the two processes which are driving the disk down within its mass.
Yeah, that's a very good point. And in fact, we completely ignored it in this exploratory model. I mean, what really should have, if we had a way to actually relate the disk ionization fraction to an alpha, it would be possible to at least estimate how this would affect it. The models that I've shown are really just to try and look at this, as I say, just the sign of the slope. There was no viscous evolution even done for this model, but that's certainly a good way to look at it. Thanks.
Actually, Richard,
if viscous evolution determines disk lifetime, it's got to have this sort of, it's got to kick in such a way that is really very efficient in bringing you down the last, I don't know, 4 orders of magnitude to go optically thin, because that's all that's measured when they say a disk lifetime. They're just looking for some optically thin something. So.
But I guess it would bring the accretion rates comparable to the photo-operation rates earlier.
Yeah, that's right. It will bring
Oh, I see.
To actually open the gap.
Okay,
Yeah.
those two rates will become
Yeah.
equal at an earlier age.
I have a question or a comment. I'm a rank amateur at this, but in Edinburgh, I remember hearing a discussion, I think, of initial disk formation for the star and disk. And I asked a question of where X-rays were important. I was told that optical and infrared set up the problem, if you will, initially. I guess when you're taking a few solar masses and 10 to the 4, 10 to the 5 years and collapsing to form a disk. Then, after a while, when the accretion slows down, you're arguing the X-rays take over, if you will, or the more dominant effect. Is that the correct picture?
Well, they take over certainly the evolution of the disk in the sense of photo operation, and that's just comparing simple photo operation rates. I mean, I would definitely, they don't take over, for example, the temperature of the dust, so they don't take over the structure of the underlying disk, because that's just mainly decided by viscous heating and from the FUV heating from the star. But they take over the evolution of the upper layers of the disk, which will then photo-operate. And they will take over, as you say, the ionization of the disk and therefore MRI.
Then the X-rays are always there, but it's also interesting to me that they're also probably working on all the later material that's coming in and accreting. There's a lot of chemistry going on. You're not discussing that. You're just talking about photoevaporation, but I'm also thinking about what it's doing to the material in the disk.
Right. So that's a kind of a separate problem.
Yes.
So the areas of the disk where we're driving the flow from, they will be mainly photodissociated already. So the chemistry will be very much affected by X-ray, and this will be the higher energy X-ray. So in fact, the X-ray, the part of the X-ray spectrum that's most important for photo operation is what we call the soft X-ray, which is basically stuff that's below 1 keV. Now, these penetrate roughly a column 10 to 22. And this is roughly where you expect now H2 to form, etc. So then it's the higher part of the spectrum, so the 2-3 keV, that actually penetrate further and can drive some of the chemistry. And so for that, there's a number of people working on this, mainly like the group of Al Glasgow and Rowan Meyerink, who actually make these models for the disk. And at that point, they actually don't care about photo operation because they are interested in lower regions of the disk. So it's almost like a decoupled problem.
Set up.
Okay, I can. Okay, thank you.
Have you plotted any of this against actual X-ray observations star by star?
Well,
Do the stars that have the more X-rays do these things more so
Faster.
or less so than the ones that have less X-rays?
So that's an absolute mess, but the one thing that we do see is that weak-line tourist stars have a couple of, well, factor of 2 roughly higher X-ray luminosities than classical tourist stars. So we have attempted to turn the argument around and to say, yeah, that's because they have lost their disks faster, and that's because photo operation is actually starving the disk from accretion by creating this gap. But at this stage, it's really, really hard to make any comparison. We've gone just as far as taking Chandra spectra and trying to construct a realistic X-ray irradiating spectrum from them. But the other thing that people have done is to try and relate neon-2 luminosities, which is supposedly created by X-ray, with X-ray luminosities. And that is also just given pretty confusing results, because while there is a general trend of higher neon-2 luminosities with higher X-ray luminosities, there's a large scatter. And that's due to the fact that, well, that's due to many reasons. You could have jets, which are confusing, and you could have accretion as well. And so accretion funnels that are creating this. So there is a general consensus that X-rays are reaching the disk and creating the neon-2 that we're seeing, but then a clean diagnostic has not been found yet, unfortunately.
Oxygen 1 might be.
That's right. And
Anyway,
so
this
this
is
is
James.
this is James' turf. Okay.
So Barbara's just laid out the basic theory that we now have developed for X-ray photoevaporation, and I'm going to talk about some of the observational diagnostics that we can use to actually probe the wind itself, rather than relying on SEDs and statistics from disk clearing timescales. So I'm going to start off with a simple picture that if you have a optically thick disk either side and you have some flow coming off the disk, then a thermally driven photoevaporative flow will have a velocity of order the escape velocity, which in T-Tauri systems will be of order a few kilometers per second. So if you make any observation of a diagnostic that's coming from within the wind, and you're looking from shallowish inclinations, then you would expect to see that emission line blue shifted by at least a few kilometers per second. And this, in fact, has been seen by Ilaria Pascucci and collaborators in the Neon 2 line. So this is just work in process observationally, as these are a few of the detected Neon 2 sources. And you can see that you find blue shifts of -6, -3, and -4. But we can do even better than that. For the best Neon 2 data we have so far, which is TW Hydra as its closest, we can fit our photoevaporation models to the data. And I fitted two models here. One is the EUV model of Font et al. And Dave Hollenbach, and the X-ray model that Barbara just mentioned. And we find that they're both exceedingly good fits. However, there's a huge difference in the photoevaporation rate between the EUV model and the X-ray model. So all Neon 2 is really telling us is that we have some flow coming off the disk. However, we can't really just tell what it is. But as already has been alluded to, there is been a problem in the literature about the neutral oxygen line, the 6300 line, and this goes all the way back to Hartigan et al. 1995, where they found resolved oxygen 1 observations around young stars, and they found lots and lots of observations with this double peaked profile, where you detect a high velocity component at a few hundred kilometers per second and a low velocity component at around 5 to 10 kilometers per second, both blue shifted. So the high velocity component was immediately attributed to stellar winds and jets. However, no immediate source was identified for the low velocity component. And they had strangely rather large luminosities, so 10 to the -5, 10 to the -4 solar luminosities. And back in 2004, when Font et al. Produced their hydrodynamic EUV wind model, they tried to fit these oxygen 1 observations with their model. And they found out the best that they could do was 10 to the -6. And the main problem for this is the fact that to produce neutral oxygen emission, you need neutral oxygen in your flow. And if you have a EUV dominated flow, then by definition it's almost going to be all fully ionized. And since hydrogen and oxygen have almost the same ionization potential, then your oxygen is going to be almost fully ionized in your flow. So the solution to this is to really have at least a partially neutral wind. So what we did once we developed our X-ray photoevaporation model was computed the ionization structure of that wind. And you can see for most of the wind region that our flow is less than 10 to the -2 ionized. So this allows us to now compute oxygen 1 line profiles and luminosities, and we find that we get up to the observed line luminosity here, 10 to the -4, and blue shifted lines varying between 10 and 0 depending on your inclination that you're looking at. I should say at the moment this is work in progress, and we suspect that this line luminosity will also vary with X-ray luminosity, but we only have one model, so we can't really say much about that yet. There have also been a few claims of non-blue shifted neon 2 emission from observations, and there are two cases where you could theoretically get that. One is the obvious one. If you're observing a close to edge-on primordial disk, then you don't expect to be looking down any of the flow, so you won't see any blue shift. And also, if you have a so-called transition disk with a large inner hole, so this is a model with an inner hole of about 20 AU, you could look, if you're looking from shallow inclination straight down the disk, you would see both the blue shifted side and the red shifted side. And again, we computed some line profiles for this, and you can see that we get a fairly broad profile, but it's pretty much peaked at 0 velocity. And there is one observation of this. This is G Omega. This is the stellar velocity, and apparently this is the line here, which shows, according to these authors, Joe Nagita, that the line isn't blue shifted. I should also mention that GM Auriga is a very messy object, and we have done no sort of exact fitting of this, but it's also quite reassuring to see that the observed high-ish inclination, or lowish inclination, I should say, disks that don't show blue shifted lines are transition disks. So it's a very short talk. So we now have good evidence for at least a partially neutral wind coming from young stellar objects. It's a few kilometers per second, so energetically we would expect that to be photoevaporation. As I've said earlier, it must be at least partially neutral in order to explain the oxygen 1 line luminosities, and this is probably X-ray photoevaporation over EUV photoevaporation. And the predicted line profiles from transition disks, as I show, can significantly differ from those of primordial disks, and we could possibly use that to test these photoevaporation models. And I wrote down some questions that we could either talk about or just think about. Can we now use these gas phase diagnostics to learn something about the transition phase? If it was photoevaporation and you're looking from high inclination, then you wouldn't expect to see a blue shift. But if it's planet formation, you've filtered out the dust, but you still have a gas disk, then you would expect to see a blue shift. I'll stop there.
I thought we have EUV and X-ray photoevaporation going on at the same time.
That's a very good question. And if I go back to this plot, our X-ray photoevaporation model does actually include EUV. And what happens is the EUV is only able to penetrate to this radius. So the X-ray wind itself is optically thick to EUV photons. Phil?
Are there in principle any other lines that might be additional diagnostics?
So there are, yes. So there are some observers who have claimed to have seen magnesium-1, I think. Yeah, and neutral hydrogen. So no, hydrogen recombination lines. So we're working on modelling those as well. We would like to have different gas phase diagnostics to probe different regions of the flow, because at the moment we're only really probing this region here, which is why we can't really distinguish between X-ray and photoevaporation models in the Neon 2, for example.
Hydrogen, you good one. Hydrogen recombination lines are being seen at the moment, and they seem to be in a different ratio with the Neon 2 line for transition disks and primordial disks, and that we're trying to see whether that matches our pictures as well, but it's work in progress.
So in your model, there should be some correlation between how inclined the disk is and how much net blue shift you get. Is that something you can look for in the data? Because most of these famous disks have some measure of inclination.
Yes. So the blue shift is a strong function of inclination, and it depends on two things. It depends on the streamline topology and on the region of the disk that it's coming from. So if you have multitudes of observations at different inclinations for the same type of object, then you would be able to proton
I
flow.
was just wondering if you plotted it. And if
Oh,
it
no.
makes sense at all.
But there are only like 6 or 7 objects. But
6 or 7 in the same sense would be good.
But
whereas
there
6 or
are-
7 randomly would be not so good. I was just wondering.
But there are very different stellar parameters, and unfortunately we only have X-ray photoevaporation models for a very small subset of the stellar parameters at the moment, but we're working on.
So if I can add to that, so there is one source that has a very strong jet, and so you can't really say anything because it's just all dominated by the jet, so it's 100 kilometers per second. And then there's 2 sources, which are, one is TW Hydra, which we plotted, and then the other, there's another one of the sources that James has found, and that has a very high inclination. So again, you can't say anything about that one because it's just Keplerian rotation. And then there's the Nagita sample, which is another 2 sources basically, if you don't count TW Hydra again. And one is GM Auriga, which has its own problems, but in any case, it's an inner hole source, and I think we can explain that non-blue shift. And then again, the other one is a very high inclination source. So we fit all the data, but that's not saying very much, unfortunately.
Yeah, I just thought if generally it was streaming out sort of the same velocity, so it was more of an inclination problem.
Right,
You
right,
might
right.
see something. I just wondered.
Yeah,
if
it's sort of the same velocity, certainly. It's between like 3 and 6, 7 maximum kilometers per second. So it's definitely all explainable with the photoevaporation, with this kind of winds. But there's a large proposal by Lara Pascucci, which I think has been approved to observe a bunch of these. And so hopefully they'll get much more data, and then that'll be much easier to say something.
Yep.
Must have comments about binary fractions. How that
Well, one.
Yeah, tuning in for the
I think Cathie's the best person to ask.
Well, I mean, people are always looking for binary companions in transition disks, and I guess there was something in the Munich meeting 2 weeks ago that I wasn't at, so I'm going to bounce it back to you because they're not very positive, the results so far, I understand.
That's right. Well, actually quite funny because they, of course, you said they, what was it, Kokutao was the first one that they looked at and they had it, and so they thought, oh, it's going to be super common. And all the talks that we saw is that they didn't find any more. So it seemed to be that most transition disks did not have a detectable binary so far. So that's the news so far.
But I mean, what if you have M stars have like more X-rays or something? You may have comments in the context of photoionization modules also. I mean, like if you see a G star and it's got an M star binary, then most of the X-rays could be coming from the it's not clear that it's I don't know. Maybe that's just.
If they're
Is there any,
if they're
you know-
the same age, they will both be emitting in the X-ray.
So
So
I think the M star would be more.
I mean, maybe that's irrelevant if you're only trying to interpret the electronics. I don't know. Maybe that's too too much complexity.
Yep.
Just a brief comment at the Chandra 10-year symposium the other month. I forget, Barbara, whether you were there or not.
no,
I was talking to Nancy Brickhouse. There's a new paper coming out on a long series of observations, and they're claiming that they have good evidence for magnetic accretion on the very interesting to compare to your models of the photoevaporation. You should talk to Nancy.
yeah, definitely.
Always.
I don't know why I'm looking
Yes,
at
the
the
always. Myriad forms of
Is that a good idea to move off? Yeah.
Sounds like a
But-